Hi, I'm Antonio Sala. In this video, we'll discuss the relationship between the best linear prediction formula, this stuff regarding the covariance matrix, and linear models with additive noise, because these models can be identified from this formula, and vice versa. If I have this model, then I can compute the covariance matrix of the joint AB vector of random variables. So let's start with our discussion. If I have two random variables, or well, in the multivariate case, two vectors of random variables, we will assume zero mean. Okay, because if it's not zero mean, we just carry out a change of variable and speak about increments with respect to the mean. So if we know the covariance matrix, so it's a symmetric matrix, the covariance between A and B is the transpose of the covariance between B and A. So well, we assume we know that. Then, in other materials, we say that the best linear prediction of A given B is this A hat, consisting on the covariance divided by the variance of the information, or in the multivariate case, covariance times the inverse of the variance matrix of B. The prediction error, the difference between A and this A hat, can be shown to have a variance given by this. The a priori variance of A is reduced by this factor arising from the information about A that B provides. If we now consider the normal distribution case, let's say, then if I know the mean and the variance, I can express the conditional distribution of A given B as a normal of mean hat A and variance sigma EA, the error of A. So if I name that thing as theta, then the conditional distribution would be a normal of mean theta B and this variance. But well, a way to generate a normal distribution with a given mean and variance is, for instance, summing to the mean, this number once I know B, an independent random variable of zero mean and the required variance. So from this expression and this expression with this definition of theta, I can build this linear model with independent additive noise that generates the conditional distribution. Of course, the actual physical model of my system need not be this linear one. In fact, nature is nonlinear dynamics. But okay, given the covariance matrix, then this model, jointly with the variance of the input to the model sigma BB, would explain that joint covariance matrix of A and B. But remember, the fact that the model explains the observed variance does not mean that this model is the true underlying physical model. Okay, now we'll see the reverse step. It's sort of the same, Imagine now that we start with an arbitrary theta, a coefficient or a matrix gain, if we are in the multivariate case. So I have a linear model whose input is a random variable of covariance matrix, or variance if it's just single dimensional, sigma BB, and this epsilon is an additive noise, statistically independent of B, with variance sigma E. So theta, sigma E, and sigma BB are known. Well, in that case, which is the joint covariance matrix between A and B? Well, let's see. The variance of A is the expected value of A transposed. Remember that we are assuming, everything zero mean. And if I carry out operations, then this product gives me 4 terms over here, say theta b times the transpose of this thing, so b transpose zeta transposed is this, and you can stop and verify operations, so we get these 4 terms in the summation. And now, as theta is a known constant, it can get out of the expectation. So for instance, the expectation of this thing is theta on the left, theta transposed on the right, and the expectation of the random variables, bb transposed. Likewise, the expectation of this is this, theta, which is a known deterministic thing, gets out of the expectation, and I get the product of random variables epsilon and b inside the expectation. Same here. Here we have it. And last, the expectation of this thing. Well, there is no theta to take out, so this is it. Then, if we assume that the additive noise epsilon and b are statistically independent, then they have no correlation, no covariance. So this thing and this thing would amount to 0. And then this is the variance of b. And this last expectation is by definition the variance of this additive noise, sigma e. So this is the variance of A given by this linear model, and the covariance, the expectation of A B transposed. Okay, then if I take out this product, then I get theta BB transposed, so I get this term, and epsilon B transposed, this term, but independence of the additive noise lets me delete this thing. So only this remains, this is 0, and this expectation is the variance of B, so there it is. Covariance is given by this expression. So if I have a linear model with additive noise, like here, relating A and B, then the joint covariance matrix of the vector of random variables A, B column is this expectation, and here we have the variance of A, and in the non-diagonal elements we have a covariance transposed here and here, and last in here we'll have the variance of the input B to the model. So we found a way, so given a model with a known theta and known variances of B and epsilon, we can build the joint covariance matrix between the model input and the model output. And to conclude, we saw in the first part of this video that given a covariance matrix, we can build a linear model with additive noise, so the parameter theta is covariance times inverse of variance of input, and the additive noise has this covariance matrix, or just variance if it's in scalar. So given a covariance matrix, we can get a linear model with additive noise, and given a linear model with additive noise, we can get a covariance matrix. So we'll finish here, and we'll see some actual numerical examples in forthcoming videos. Thanks for your attention.